Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be starting mathematical proof, which is different from mathematical computation. Up until now we've been doing mostly computation problems. How many of this, how many of that, find the number, use inclusion, exclusion, and count something. Now we need to turn to how do we actually come up with formulas like inclusion, exclusion, or Gauss's formula. How do we prove them rigorously and know that they're always correct? One of the most powerful forms of proof in combinatorics is induction, which is a good method of proof for dealing with positive integers. So that's what we're going to start with today. But we're also going to just motivate why do we need mathematical proof to be certain of things. So let's start with an interesting example called Polya's problem. Are there always more numbers between 2 and n that have an odd number of prime factors than even? Here I've made a table of the numbers from 2 to 12, along with their prime factorizations in the second column, and then in the third column we just count how many primes are in the factorization and say whether that's odd or even. So primes like 2, 3, and 5 just have one prime in their prime factorization, so that's odd. But then 4 is 2 times 2, so there's an even number of primes. 8 is 2 times 2 times 2, that's an odd number of primes, and so on. In this table, we see that there's more odds than evens listed here from 2 up to 12, and in fact, if you stop at any point, like up to 8, there's more odds than evens up to that point. And Polya asked, does this pattern always continue? Is it always more likely to have an odd number of prime factors than even up to any given point starting at 2? So, interestingly, if one calculates this table down to 900 million, n equals 900 million, then there are more odds than evens at every step. So that seems like it's probably true forever. If things are true up to 900 million cases in science, we say, yep, that's a true fact about how the world works. So at this point, we might conjecture that it's always true, but there is a counterexample. A counterexample is an example that proves a conjecture wrong. So a conjecture is something that you think is true, but you don't have a proof for yet. Maybe you have a lot of evidence for, but when you find a counterexample, then you know that that conjecture is false. The counterexample is at 906,150,257. That's the first time that the number of numbers less than that number, having an even number of primes, is bigger than the number with an odd number of primes. So it does outweigh it at that point, and actually there's lots of counterexamples. That's not the only counterexample out there. But it takes up to this number for it to be false. So sometimes mathematical patterns can seem to be true, but they're not. They're not in general because there is some counterexample way out here above 900 million. So just because a pattern looks true for the first 900 million cases doesn't mean it's always true. We need proof to see whether something we think is true is always true. So let's look at another pattern that is actually true, that does repeat forever, the sums of odd numbers. So we know 1 is just 1, and 1 plus 3, the sum of the first two odd numbers, is 4. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 16. If you add the first 5 odd numbers, it's 25, and if you add the first 6 odd numbers, it's 36. The pattern you might notice here is that this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. So the sum of the first n odd numbers appears to be n squared. Let's make that our conjecture. Now, one thing you could do is try to find a counterexample, see if you calculate out more examples, but if you can't find a counterexample, you can try to prove it. And a great method for proving this kind of statement is proof by induction. So here's the idea informally first. We want to check that if we add the n plus first odd number to n squared, we get n plus 1 squared, because then that would mean the pattern continues. If we add 15 to the sum of the first 6 odd numbers up to 13, do we get the next square? Do we get 7 squared or 49? Given that we had that there was 36, maybe we can show that the pattern has to continue because you can build off the previous example. So let's investigate this. First of all, how do we write the n plus first odd number? Well, the first odd number is 1, which is 2 times 1 minus 1. The second odd number is 3, which is 2 times 2 minus 1. The third odd number is 5, which is 2 times 3 minus 1. So it looks like the kth odd number is 2 times k minus 1. So the n plus first odd number is 2 times n plus 1 minus 1, or 2n plus 1. So what we want to do is add 2n plus 1 to the previous sum, which we know is n squared, and see if it's n plus 1 squared. Because then, as long as the previous step you got n squared, the next step you'll get the next square, and then the next step you'll get the next square, and so on, no matter what n is. And that means that the pattern has to continue forever. So let's check this. N squared plus 2n plus 1 is actually n plus 1 squared, because if I take out the parentheses, that factors as n plus 1 squared. And so yes, the pattern continues forever, and informally here we have a proof. Now let's go through the steps of induction to make this a little more rigorous. So mathematical induction is the axiom of mathematics which is something we all assume to do mathematics together and agree on things, that says if P sub n is a statement about positive integers n, like the sum of the first n odd numbers is n squared, here's an example of P sub n, then suppose you can prove these two following things. Suppose P sub 1 is true, so the first case is true, that's called the base case, and then also show that for any k, if pk is true, then pk plus 1 is true. Then you can conclude that Pn is true for all n. It is important that you choose a different variable k here if we're talking about the induction step than n, because what we're doing is a little mini proof. We're not proving the entire thing in the induction step. What we're saying is that you want to show that if pk is true, then pk plus 1 is true, even if you don't know if pk is true. You just want to show that it implies it, because then starting from p1, p1 implies p2, which implies p3, which implies p4, and you get that the statement is true for all the positive integers. So let's do, in this case, to make it more rigorous, our base case is just the sum of the first odd number is 1 squared. And for the sum of the first n odd numbers, we want to now let k be an arbitrary positive integer, bigger than or equal to 1. And so for any k, we want to show that if the first k odd numbers sum to k squared, then the first k plus 1 odd numbers sum to k plus 1 squared. So that was what we were doing informally on the last slide. So how do you prove that inductive step rigorously? An if-then statement always goes like this. You assume the first statement and then you prove the second statement. So let's break down this induction principle, which the statement is for any k, if pk is true, then pk plus 1 is true. So first, you just let k be an arbitrary integer. You can just literally write this sentence down in your proof. That's already an important step. It's just declaring k to be an integer, like declaring a variable or typing a variable in computer science. And then you assume pk, and you can use pk because you assumed it. You can use that to try to prove pk plus 1. If you can do that successfully, that means that the assumption pk, called the induction hypothesis, implies pk plus 1, and you've proven the statement of induction. So let's apply this to our example. We want to show in our induction step of our proof that for any k, if the first k odd numbers sum to k squared, then the first k plus 1 odd numbers square to k plus 1 squared. So what we do is we let k bigger than or equal to 1 be arbitrary, assume the sum of the first k odd numbers is k squared, and then we already know the k plus first odd number is 2 times k plus 1 minus 1. That was the computation we did before, and that's 2k plus 1. So adding that to k squared gives the sum of the first k plus 1 odd numbers, and the total is k squared plus 2k plus 1, which is k plus 1 squared, so the sum of the first k plus 1 odd numbers is k plus 1 squared. So we've assumed pk and proved down here pk plus 1, and you notice it does take some computation in the middle. So there's going to be some actual thinking to do in the step between assuming pk and proving pk plus 1 in general. That's the hard part. So putting it all together, here's how you would write up a formal proof by induction. Proofs are written essay style in mathematics. We usually write them in English. You don't just write a bunch of lines of computation like we do in computation math problems. We actually write a story. A proof is an explanation for a reader to understand your logic. So what you do is you write a theorem first, and then you write proof, and you write your proof below that. And what it should look like is you state the theorem, the sum of the first n odd numbers is n squared for any positive integer n. And for proof, you can first tell the reader that we're going to be using the method of mathematical induction. You can say, we proceed by induction. We always use we when we write proof, not I, or you, or he, or she, or any other pronoun. We use the royal we to include the reader in our proof that we're going through together. So we say we proceed by induction. For the base case, the sum of the first one odd number is 1, which is 1 squared. So you can just write out the base case in a little tiny proof there. It's usually just a simple computation, and we've done the base case. And now you can say for the inductive step, this tells the reader that, oh, we're on that second step of induction. So we do the steps of induction. Let k bigger than or equal to 1 be arbitrary. And now we do the second step and assume that the sum of the first k odd numbers is k squared. Then we have to do some of our calculation here, and we do it in English. Then the k plus first odd number is 2k plus 1 minus 1, which is 2k plus 1. And so the sum of the first k plus 1 odd numbers is formed by adding 2k plus 1 to k squared. This is where we're using this assumption that the sum of the first k odd numbers is k squared, and we're just adding the next one. This gives k squared plus 2k plus 1, which factors as k plus 1 squared as desired. We say as desired because that's what we wanted to show, that the first k plus 1 sum to k plus 1 squared. So we've completed the steps of induction. So we can write QED, which is an abbreviation for quod erat demonstrata, which is Latin for as we wish to show. Or you can just write a little square to indicate that your proof is done. But usually there's just some symbol you write. You can write a smiley face or a star, or whatever you like, to indicate that your proof is done. There's one more variant on induction that we'll use in this course, which is strong induction. So it's actually equivalent to the statement of induction. You can show they're the same logical statement. But sometimes it just helps the ease of writing up the proof when you phrase it in this way. So strong induction says let P sub n, again, be a statement about positive integers. And you suppose the base case P1 is true again, that's the same. And also you need the strong induction step, which is for any k bigger than or equal to 1, if Pj is true for all j less than or equal to k, then pk plus 1 is true. So the difference between this and ordinary induction is ordinary induction only assumes pk is true and uses that to prove pk plus 1. But this one says you can actually assume p1, p2, p3 up to pk are all true and use that whole set of facts to try to prove pk plus 1. And it just gives you a little bit more powerful information to work with to try to get to the next step for the induction to go through. So here's a good example of a statement that's easier to prove using this strong induction model, which is any tree on n vertices has n minus 1 edges. Now what's a tree? A tree is a connected graph with no cycles. So here's a tree. It's a graph which has nodes and edges that doesn't have any cycles. I never loop around in a continuous path that goes back to the same vertex. So any tree on n vertices has n minus 1 edges is what we're claiming, and we want to prove this by induction on the number of vertices. So we first look at the base case, a tree with one vertex. The only tree with one vertex is the single tree with 0 edges, and so that has 0 edges, which is 1 minus 1 edges, and so the base case holds. So for the strong induction step, this is just an informal outline of how we would do the reasoning. What we want to do is to prove it for size n, we assume it's true for all trees with smaller numbers of vertices. And then we use that fact to prove it for our big trees. So given a tree with n vertices, remove any edge. So here's this dotted edge we decided to remove here. And if we cover up that edge, it makes two different trees because you can't get a cycle from removing an edge. So these are both still two trees, and they're also disconnected because I couldn't have connected them, say, along another edge here, because that would have made a cycle in the original tree. And so if you remove an edge, you get two disconnected trees, and each one of them, by our strong induction hypothesis, we know how many edges they have. If this one has k vertices and n minus k vertices over here, then there's k minus 1 edges on the left by induction, and n minus k minus 1 on the right. We add these two together to get the total number of edges in the two subtrees, and we add 1 for that missing edge that we add back to see how many edges are in our whole tree. And if you add these all together, the k's cancel, and we see that this is just n minus 1. And so that completes the induction. So now you try. Prove Gauss's lemma rigorously using induction. This should be similar to the sum of odd numbers example. So you want to prove that for all n bigger than or equal to 1, the sum 1 plus 2 plus 3 up to n is n times n plus 1 over 2. And that's all for today, and I'll see you next time.